All right, so today I'm here to answer the question, can low-cost batteries help us to use more renewables and build fewer transmission lines? The answer is yes. And the question, so really that's an obvious thing. Of course I'm going to say yes, right? But the thing we're really more interested in is why is this a question at all? There's a couple of really simple ways to explain this, and it becomes more complex, but these two things for this day is a reasonable way to start. First of all, renewables are messy. They're very intermittent. We want, as consumers, a continuous source of power that comes on whenever we need it and goes off whenever we don't need it. And if you combine that with the idea that electrons or electricity is about the only commodity used at bulk, massive quantities that is not stored in some way or other typically, it means that we have to have a sort of constant or adjustable power supply. And renewables don't play like that. They jump all over the place. This plot here on the right shows a year's worth of wind data, and it's very jagged. You see it. This is from an aggregated wind farm. And it goes from nearly zero on some days or hours all the way up to, in some cases, as much as 6 gigawatts. That's a huge bit of variability. So we want to be able to figure out how to harness this most effectively. And certainly just trying to use this as it's coming out in such a jagged fashion is not an appropriate answer. Solar power is similar. It has very jagged daytime depending on what kind of cloud cover we have and what's going on. And of course it's dark at night, and that darkness is a real problem for that technology. So no matter how much solar we put up, we get nothing at nighttime. So we need some way to store the energy and then give it back in times of other need. The other question is more about transmission lines. And the electricity grid is old. It has bottlenecks and needs to be extended. So this picture here on the left is what most of us are presented with when we think about a cartoon of what the energy grid actually looks like. There's the generation station, there's some transmission very neatly laid out, there's substations, distribution stations, there are residential communities, and there's a line connecting them all, right? Very simple. The reality is very different. This is a schematic of part of the United States power grid. And what you see is that there's these sort of clumps of use where you can imagine a lot of cross-sharing between the different generation sources. Each dot is a generation source, for example, and these are the major transmission lines. But there are other places where it's very tenuous. You see here and down here, etc. And you can imagine that if a population shifts or if something happens, someone builds a large factory somewhere that strains this, you want to transfer energy from one resource to another. Perhaps you can't at the right time of day, right? If you had storage, maybe you could. If you put it right next to one of these major transmission lines, if you put a big battery, say here, for example, you can continually charge it during off-peak hours, and then when demand is highest at that point, you can pull from the battery instead of the grid line, which means you don't have to build a bigger line. You can use some other asset to give you the same outcome. So that is how a battery would do. That's why it's a question, right? So what does the answer look like? What does a battery look like that might do this? We're already using a lot of pumped hydro in the world. This is where you pump water up a hill, put it in a reservoir at one point, and it comes down through a turbine at another point when you need it. Very cheap, very bulk storage. But unfortunately, most of these locations where this is applicable have been implemented, right? And it's difficult to build dams. Right now, you often will submerge valuable natural resources or villages or towns or whatever. So there needs to be a more portable way of doing this. And to that end, we get to a couple options. One is compressed gas, which you might do underground, subterranean compressed air. Also an interesting option. Also site-specific. In fact, recently there was a site they put in many millions of dollars to figure out, even if it was a legitimate site, there's a lot of hope, didn't pan out. So again, very site-specific. So what I'm interested in is what is portable. We can put anywhere we need that's very low cost that will last a long time. And so here's an example too, and this is work that I collaboration with Professor Jay Abt, and this answers the age-old question: what do you do if you combine a material scientist and a retired astronaut and let them do some work together? You end up answering the question about how much wind you can put on with different size batteries when combined with the fast-ramping natural turbine. The answer is it really matters. If you have a 100 megawatt natural, I'm not going to go through these details at all because it's a bit complicated, but to explain these two plots. But the key thing I'll draw your attention to is the point down here. The lowest point is the average cost of power, net present value in dollars per megawatt hour that you can get. If you have zero wind energy and just a gas turbine, it's yeah, $55, $60 per megawatt hour. And the other thing is that if you put in the right size battery and you want to get a lot of energy from a wind instead of a natural gas because of a variety of incentives, or just there's reasons to do this for a lot of reasons, it turns out that you can get almost the same price point if you have a reasonably sized battery, in this case a 21 megawatt hour sodium sulfur battery, and you can have up to 30% wind penetration, right? So 30%, you've now swapped out 30% of the gas you were burning for wind, free, clean wind, if you put a battery in place in the middle of all of this, right? That's an exciting answer. So the question is, well, what do these batteries look like? There are a lot of constraints. They got to be really cheap. They got to be cheaper than anything we're making right now. $200 a kilowatt hour at capital cost, so if I put in a 10 megawatt hour system, it's still going to cost a lot of money, and it has to last more than 10 years. You have to amortize that cost over a long period of time. And so to get to this really low cost, what's it look like? What does that be? What's it made of, right? Really abundant low-cost materials with simple manufacturing, a simple balance of system. That is to say, the stuff that controls it also has to be really simple and inexpensive. It's got to be very environmentally adaptable and benign, edible, or at least very easy to dispose of, not hazardous, not flammable, and a very long lifetime. Again, those customers who are serious about doing very large-scale storage also take the long view. What if this lasts 20 years, right? What is the overall value I get on a daily basis if this operates for 20 years? How do I make that happen? And it's got to be completely reliable, just as though we rely on the grid on a daily basis. If the battery fails, something will go wrong. It must work. And so this was the approach that I took, started CMU, and there's been a spin-off company. I'll tell you just one sentence on that in a second. We have a menu of viable materials, and these are these sort of combinations of extremely common low-cost things. And then you have to go through a series of steps with these materials. If you're going to work with these, and this is what really you have to pick from if you're going to do this, because it's a vast question. These are huge kinds of things, of objects, and the only way you can make this work is if you have this kind of stuff. And it has to be not that pure, because any of these, if they're too pure, also cost a lot of money. So it's a cost gate on that. And then you assess what you would do and how you would manufacture with the materials, and you have to do a cost gate on that. So you have to think about how would I use these. And then you assess the performance of how these might function in a battery, and the performance is assessed against key things, the marketplace, dollars per kilowatt hour. Is it reliable? Is it safe? Right? So all of this comes together and resulted in, after a fair amount of poking and prodding in my lab in 2007 and 2008, to a really simple battery idea. It's an aqueous electrolyte sodium-ion battery. It's got very low-cost carbon as one electrode and a manganese oxide material on the other, on the cathode side, the plus side, that can accept and reject sodium ions. So when you charge the battery, the sodium goes in the carbon. When you discharge it, it goes back in the manganese oxide. And these things are very inexpensive. And the kicker is the electrolyte is sodium sulfate and water, so it's essentially a salt water. And this is a preservative we use in the food industry. And the separator itself is essentially very low-cost synthetic cotton. So everything in this device was incepted and put together and designed to be cheap and long-lasting. And it doesn't have very good energy density. It could never be used in a car. It's not that good for a lot of mobile applications. But if you want something to sit there and last a long time and just function, this is maybe an option, right? And so the innovation part goes like this, right? You get something really tiny in a lab that works. You have a lot of research group, and you get it's a little button cell. It's about this kind of thing that goes in your watch. We can make these, and you test them, and it looks appealing. And you say, well, if I can make 1 trillion of these, I can change the world, right? Of course, you can't. So you spend 16 months in a lab trying to understand what it might look like to get bigger. And then you realize that you need more help, that you can't do it out of a university, that this is going to require a bigger effort. And mind you, I can certainly vouch for this firsthand, you don't do a manufacturing-based energy startup to become really rich, right? That's for the web people, right? This is a different thing altogether. The amount of capital it requires to really do this is profoundly large, and the amount of time it takes is very long. And you've got to be willing to go for the long haul, and it may or may not work, right? So we're towards the middle of our long haul, and things are looking good. But this is not a get-rich-fast scheme whatsoever. In early 2010, we got some substantial venture interest and started a spinoff here down in Lawrenceville. And our first sort of objects got a little bigger, about this big, little bread box size things, and they're pretty good, pretty interesting, and that leveraged some more funding, some more interest, and then we were sort of building these objects now. They're about this tall, about this big, about just over a kilowatt hour of capacity, and they can be put together in pallets and stacks and in residences or in buildings and so forth, and we're shipping this. And we're doing all of these things right now up until next year here in Lawrenceville, and we're opening a factory next year in Westmoreland County. We currently employ just over 100 people, and by next year we'll be over 200 people. We've made a lot of jobs, and we've brought in a fair amount of state money, local money, federal money, and venture cap to the region. And I think this is really having an impact, and it's kind of exciting to have been a part of it. And Carnegie Mellon was extremely instrumental in this, and the interdisciplinary work here has been fantastic in letting this happen. And I thank the university as a whole for all the support. Thank you. So yeah, I mean, and that's really it. I mean, we're just finishing one of our DOE projects. We have demonstrated now a over 1,000-volt grid-tied unit that is giving and taking from the grid, buying and selling. It's a huge proof of concept, and it gets us to grid scale, local grid scale voltages, and shows good performance. And this just gives you an idea. We put those modules together in pallets or containers or even much larger arrays. And we're now negotiating with major customers who want many, many tens or hundreds of megawatt hours of these to be put in. And this is the scale. This is the inside of our factory right now. This was taken last week in Westmoreland. You can see we're just starting to put in some walls. We gutted this. This is the old Sony plant. It was an old automotive manufacturing plant before that. We're taking a fraction of it right now. We're about 350,000 square feet, but it's going to grow. And next year, this is going to be populated with a lot of really interesting equipment. So stay tuned, and I'll tell you how it goes. Thank you.